Welcome to Tedious Science, fellow explorers, where curiosity meets the infinite expanse of space and wonder, takes the scenic route through our solar system. I'm genuinely thrilled you found your way here to this gentle journey through some of the most mind-bending, absolutely incredible facts about our celestial neighbourhood. Now, before we embark on this adventure together, I'd love to know where in the world you're listening from tonight, and what time is it in your corner of the universe? There's something beautifully fitting about that question, isn't it? Here we are, scattered across time zones, each arriving at this moment from our own unique vantage point in space. If you find this cosmic voyage intriguing, enlightening, or just a pleasant way to explore the wonders above, I'd be ever so grateful if you gave this video a like and perhaps subscribed. It helps this little corner of astronomical calm reach others who might need a peaceful pause to marvel at the universe around us. And I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll have learned something extraordinary about our solar system before drifting off to sleep. So settle in, let your imagination soar, and let's begin this gentle exploration. Because scattered throughout our solar system are phenomena so bizarre, so counterintuitive, and so absolutely remarkable that they sound like pure fiction. But every single one of these cosmic curiosities is completely, wonderfully real. Let's start with something that sounds like it belongs in a fairy tale. There are places in our solar system where it literally rains diamonds. I'm not speaking metaphorically here. On Neptune and Uranus, deep within their atmospheric layers, the pressure becomes so intense that carbon atoms from methane molecules are crushed into actual diamonds that fall like glittering precipitation through the planet's interior. Scientists have recreated these conditions in laboratories using high-powered lasers, successfully transforming hydrocarbons into diamond crystals under pressures millions of times greater than what we experience on Earth. These diamonds likely don't survive their entire journey, eventually melting or dissolving as they sink deeper, but the process itself is continuous, creating a perpetual shower of the universe's most precious stones in the most distant corners of our solar system. Moving closer to home, let's talk about Venus, our neighbouring planet that seems determined to break every rule we think we understand about planetary behaviour. Venus spins so slowly that a single day there lasts longer than an entire year. It takes Venus about 243 Earth days to complete one rotation on its axis, but only 225 Earth days to orbit the Sun once. Imagine trying to schedule a meeting on Venus where the day you planned it on hasn't even finished by the time your yearly anniversary rolls around. But Venus doesn't stop there. With its peculiarities, it also spins backward compared to most other planets in our solar system. If you could somehow stand on Venus's surface, ignoring the crushing pressure and sulfuric acid clouds, you'd watch the sun rise in the west and set in the east. It's as if Venus decided to be the rebel of the planetary family, doing everything in reverse just to keep things interesting. Now here's something that might make you look at Saturn differently the next time you see it through a telescope. Despite being a massive gas giant that's 95 times more massive than Earth, Saturn is so light that it would actually float in water. Its average density is only about 0.687 grams per cubic centimetre, which is less than water's density of 1.0. Of course, you'd need a bathtub the size of a planet to test this theory, but the physics checks out perfectly. This remarkable lightness comes from Saturn being composed mostly of hydrogen and helium, the lightest elements in the universe. While its volume is enormous, spreading this relatively low-mass material across such a vast space creates that surprisingly low density that makes Saturn the cosmic equivalent of a giant, beautiful soap bubble. Speaking of cosmic phenomena that challenge our earthbound intuition, let's journey to Jupiter, where storms can rage for centuries. The Great Red Spot, that iconic swirling tempest in Jupiter's atmosphere, has been continuously observed for over 400 years. This is a storm so large that 2 or 3 Earths could fit comfortably inside it, with wind speeds exceeding 400 kilometers per hour. What makes this storm so persistent is Jupiter's lack of solid surface and its enormous internal heat. On Earth, storms are broken up by mountains, oceans, and changing temperatures. But Jupiter's storm sits between two powerful jet streams that trap it in place, like a cosmic prison of perpetual motion. It's been slowly shrinking in recent decades, but it remains active, a testament to the incredible forces at work in our solar system's largest planet. Let's drift now to one of the most poetic discoveries in space science. There's a point between Earth and the Sun where gravity balances perfectly, and that's where we place telescopes to watch the cosmos. This location, called Lagrange Point 1, sits about 1.5 million kilometers from Earth in the direction of the Sun. Here, the gravitational pull of Earth and the Sun cancel out in such a way that objects can maintain a stable position relative to both bodies. It's like finding the perfect cosmic parking spot where spacecraft can stay put with minimal fuel, continuously observing the Sun or peering into deep space without interruption. The Solar and Heliospheric Observatory has been stationed at this point, monitoring the Sun 24/7 and helping predict solar flares that might affect Earth. It's a beautiful example of how we can use the universe's own physics to our advantage. Now here's something that might surprise you about time itself in our solar system. Mercury experiences some of the most extreme temperature swings imaginable, ranging from negative 170 degrees Celsius at night to plus 430 degrees Celsius during the day. This incredible variation happens because Mercury has virtually no atmosphere to trap heat. Once the Sun sets, heat escapes into space so rapidly that the surface becomes colder than anywhere on Earth. But here's the truly mind-bending part. Mercury's day, from sunrise to sunrise, lasts about 176 Earth days. That means each side of the planet endures almost 3 Earth months of scorching heat, followed by nearly 3 months of bitter cold. It's like the universe's most extreme example of seasonal affective disorder. Let's talk about something that sounds like science fiction, but is happening right now. The Moon is slowly moving away from Earth at a rate of about 3.8 centimeters per year. This has been measured with incredible precision using laser reflectors left behind by the Apollo missions. The reason is tidal interaction. Earth's gravity pulls on the Moon, and the Moon pulls back on Earth's oceans, creating friction that transfers rotational energy. As a result, not only is the Moon drifting away, but Earth's rotation is gradually slowing down. Days are getting longer, though at a rate so slow you'd never notice. Hundreds of millions of years ago, during the age of dinosaurs, a day lasted only about 23 hours, and the Moon appeared much larger in the sky. This cosmic dance between Earth and Moon has been shaping our planet's rhythm for billions of years. Here's something that beautifully illustrates the interconnectedness of our solar system. Jupiter acts like a cosmic shield, deflecting dangerous comets and asteroids that might otherwise threaten Earth and the inner planets. Its immense gravity can capture, redirect, or eject these potentially hazardous objects. We've actually witnessed this protective role in action, most famously when comet Shoemaker Levy 9 broke apart and collided with Jupiter in 1994, leaving huge scars in the planet's atmosphere. Without Jupiter's gravitational influence, Earth would likely experience far more catastrophic impacts. It's as if our solar system has its own built-in security system, with Jupiter standing guard at the gates of the inner planets, quietly protecting us from cosmic debris that could otherwise alter the course of life on Earth. Now let's venture to the outer edges of our solar system, where even Pluto holds surprises. Despite being incredibly far from the Sun, where temperatures plummet to negative 230 degrees Celsius, Pluto may still harbour liquid water beneath its icy crust. This possibility is supported by data from the New Horizons mission, which revealed surface features suggesting geological activity. The mechanism behind this potential underground ocean involves radioactive decay in Pluto's rocky core, providing just enough heat combined with insulation from thick layers of ice to keep water liquid. If confirmed, this would add Pluto to the growing list of worlds in our solar system that might harbour hidden oceans, expanding our understanding of where liquid water and potentially life might exist. Here's something that sounds like poetry written by the cosmos itself. Saturn's North Pole features a perfect hexagonal pattern, a six-sided jet stream about 30,000 kilometers wide, larger than Earth itself. This geometric precision appears not in solid rock or ice, but in fast-moving gas, maintained by forces we still don't fully understand. The hexagon has been stable for decades, rotating with the planet and never drifting or fading. While laboratory experiments with rotating fluids have created similar polygon shapes, Saturn's hexagon remains one of the most unusual and unexplained structures in our solar system. There's no hexagon at Saturn's south pole, making this northern phenomenon even more mysterious. Let's talk about Titan, Saturn's largest moon, which has rivers, lakes and rain, but all made of liquid methane. At Titan's extremely low temperatures, methane behaves exactly like water does on Earth. It evaporates, forms clouds, and rains back down, creating a complete methane cycle with seasonal weather patterns. Titan has dark streaks across its surface, suggesting recent rainfall, lakes hundreds of kilometers wide, and even seas of liquid methane bigger than the Great Lakes combined. It's the only moon in our solar system known to have stable liquid on its surface, creating landscapes that are eerily familiar yet utterly alien. The Cassini spacecraft discovered that one of these methane seas is at least 300 meters deep, with possible islands that appear and disappear, perhaps floating chunks of ice. Here's something that challenges our perception of the asteroid belt. Despite being home to hundreds of thousands of known asteroids, the belt between Mars and Jupiter is mostly empty space. The asteroids are separated by millions of kilometers, and a spacecraft flying through would most likely see nothing nearby. Hollywood's dramatic scenes of ships dodging asteroids are far from reality. The belt is so sparse that multiple spacecraft have crossed it safely without incident. The total mass of all asteroids combined is less than 5% of our moon's mass. It's not the dense field of debris often imagined, but rather a structured, stable region of scattered objects, each following its own lonely orbit through the vast emptiness of space. Let's journey to Uranus, where something truly extraordinary happened in the planet's past. Uranus rotates on its side, with an axial tilt of about 98 degrees, meaning it's essentially lying down relative to its orbit. Its moons orbit in this same tilted plane, as if the entire system was knocked over by some cosmic collision in the ancient past. This extreme tilt causes the most unusual seasons in the solar system. During parts of Uranus's 84-year orbit, one pole points nearly directly at the Sun, while the other experiences decades of darkness. The planet's moons follow this tilted rotation, orbiting around what appears to be a sideways planet, creating one of the most asymmetric systems we know. Here's something that beautifully demonstrates the solar system's dynamic nature. Our entire solar system orbits around the center of the Milky Way galaxy in a journey that takes about 225 million years to complete. This means the last time we were in our current galactic position, dinosaurs didn't exist yet. We're all cosmic travelers, moving through space at about 828,000 kilometers per hour. Though the journey is so vast, we complete only about 20 full orbits in the Sun's entire lifetime. As we travel through the galaxy, we encounter different regions of space, varying densities of interstellar material, and changing cosmic ray environments. Our position in the galaxy influences everything from the meteor shower patterns we observe to the background radiation that bathes our solar system. Let's talk about something surprisingly common yet largely invisible. Earth actually shares its orbit with small asteroids called Trojans that travel with us, staying in stable gravitational zones 60 degrees ahead and behind our planet. These cosmic companions are difficult to see because they are always positioned close to the Sun's direction from Earth's perspective. The first Earth Trojan was discovered in 2010, a 300-metre wide asteroid following a tadpole-shaped path around its stable point. More likely exist but remain hidden in the Sun's glare. These objects offer us nearby targets for future space missions and represent primordial material from the early solar system, preserved in Earth's own orbital neighbourhood. Here's something that illustrates the incredible precision of cosmic mechanics. There are regions in space where combined gravitational and orbital forces allow small objects to stay relatively fixed with respect to two larger bodies. These Lagrange points create cosmic parking spots where the James Webb Space Telescope now sits, always facing deep space while staying in communication with Earth. These points represent perfect mathematical solutions to the complex gravitational dance between massive objects, creating islands of stability in the chaotic dynamics of orbital mechanics. They're not just theoretical concepts, but practical locations we use for some of our most important scientific instruments. Now here's something about Mars that connects it intimately to Earth's experience. Mars has seasons just like Earth, caused by its similar axial tilt of about 25 degrees. However, because Mars takes about 687 Earth days to orbit the Sun, each Martian season lasts roughly twice as long as Earth's seasons, but Mars adds its own dramatic flair to seasonal changes. During winter, carbon dioxide from the atmosphere freezes at the poles, and in summer, this CO2 sublimes back into gas, causing planet-wide dust storms that can last for weeks and sometimes grow to cover the entire planet. These storms are driven by seasonal heating differences and can be so intense they block sunlight and affect surface temperatures globally. Let's explore something that challenges our understanding of planetary formation. The region between Mars and Jupiter, now occupied by the asteroid belt, could have been where a planet tried to form but failed. The gravitational influence of nearby Jupiter disrupted the accretion process, preventing the material from coalescing into a single world. Instead of one planet, we have thousands of fragments, asteroid families that are groups of pieces from larger parent bodies that were broken apart by collisions. Some of these asteroids, like Vesta and Ceres, represent what early protoplanets might have looked like. Ceres is even classified as a dwarf planet and shows signs of past geological activity, including bright salt deposits that suggest recent movement of briny water beneath its surface. Here's something that beautifully illustrates the universe's tendency toward geometric perfection. Hyperion, one of Saturn's moons, tumbles chaotically as it orbits, never showing the same face to Saturn twice. Its irregular, sponge-like surface and unpredictable rotation make it one of the most unusual objects in our solar system. Unlike most moons that are tidally locked to their planets, Hyperion's shape and gravitational interactions with nearby Titan cause it to tumble randomly. Its low density and porous surface create deep, sharp-edged craters that give it an appearance often compared to a natural spacecraft or cosmic sponge. Let's talk about something that demonstrates the power of our modern technology. Scientists can now peek into dreams and decode some visual content using brain activity patterns. While we can't watch someone's dreams like a movie, researchers have successfully identified categories of images people are dreaming about with about 60% accuracy. This represents just the beginning of understanding the dreaming mind. The implications extend far beyond curiosity. For people with communication disorders, future dream reading technology might provide access to their inner worlds in ways never before possible. Here's something that shows how our solar system extends far beyond what we can easily see. Long-period comets arrive from the Oort cloud, a distant region that may extend up to 100,000 astronomical units from the Sun. These ancient travellers take thousands or even millions of years to complete one orbit, appearing suddenly in our skies with no warning. When they do arrive, they bring with them material unchanged since the formation of the solar system, like time capsules from the cosmic deep freeze. Some famous examples include Comet Hale-Bopp and Comet Neowise, visitors from the solar system's most distant frontier. Now here's something that demonstrates the incredible violence that can occur in space. Some comets, called sun grazers, follow orbits that take them so close to the Sun that they're destroyed by the intense heat and radiation. Most don't survive the journey, vaporizing completely as they approach our star. Space-based solar observatories have captured hundreds of these cosmic death spirals, watching as comets heat up to thousands of degrees and disintegrate in real time. These events, while brief, provide valuable insights into both solar behavior and the composition of these ancient ice balls. Let's explore something that reveals the dynamic nature of planetary systems. Natural satellites can actually turn into rings if they get too close to their host planets. When a moon crosses what's called the Roche limit, tidal forces become stronger than the moon's own gravity, literally tearing it apart. This may be how Saturn's magnificent rings formed from a former moon that wandered too close and was destroyed. The process works in reverse too. Ring particles can clump together and form new moons, creating a cosmic cycle of destruction and creation that has shaped planetary systems throughout the universe. Here's something that shows how even the most distant worlds can surprise us. Triton, Neptune's largest moon, orbits in the opposite direction of its planet's rotation, strongly suggesting it was captured from elsewhere in the solar system. This backward orbit creates tidal forces that are gradually shrinking Triton's orbit. Eventually, Triton may get so close to Neptune that it will be torn apart, potentially creating a new ring system around the ice giant. It's a reminder that even in the outer solar system, dramatic changes continue to unfold over cosmic timescales. Now let's talk about something that illustrates the interconnected nature of our cosmic neighborhood. The heliosphere, a protective bubble created by the sun's solar wind, shields our entire solar system from external radiation. This invisible barrier deflects galactic cosmic rays and creates a region where solar influence dominates. The boundary of this protective bubble, called the heliopause, has been crossed by both Voyager spacecraft, providing direct measurements of the transition from solar-dominated space to the interstellar medium. It's like discovering the exact edge of our solar system's sphere of influence. Here's something that demonstrates the precision required for space exploration. GPS satellites must account for both special and general relativity to maintain accuracy. The satellites experience time differently due to their speed and their position in Earth's weaker gravitational field. Without correcting for these relativistic effects, GPS would be wrong by several kilometers every day. It's a beautiful example of how Einstein's seemingly abstract theories have very practical applications in our daily lives. Every time you use GPS to navigate, you're benefiting from our understanding of how time and space behave under different conditions. Let's explore something that shows how life itself is connected to cosmic processes. The moon helps stabilize Earth's axial tilt, preventing chaotic variations that could reach up to 60 degrees, according to some models. This stability has been crucial for maintaining the relatively stable climate that allowed complex life to evolve. Mars, which lacks a large moon, experiences much more dramatic changes in its axial tilt over geological time. The moon's stabilizing influence is one of the many factors that make Earth uniquely suitable for life as we know it. Here's something that illustrates the extreme environments that exist in our solar system. Venus's atmosphere is so dense and corrosive that spacecraft can only survive on its surface for minutes to hours before being crushed or corroded. The Soviet Venera landers, the only successful Venus surface missions, lasted at most about 2 hours in conditions that include crushing pressure, sulfuric acid clouds, and temperatures hot enough to melt lead. Despite these hostile conditions, Venus remains scientifically valuable because its similarities to Earth help us understand how planets can evolve along very different paths. It's a cautionary tale written in atmospheric chemistry and planetary physics. Finally, let's end with something that brings our journey full circle. Light from the sun takes about 8 minutes to reach Earth, which means we always see our star as it was 8 minutes ago. This simple fact connects us to the fundamental nature of the universe. We never see anything in real time because light has a finite speed. Every photon that touches your skin, every ray of sunlight that warms your face, began its journey 8 minutes ago from a nuclear furnace 150 million kilometers away. It's traveled through the vacuum of space at the fastest speed possible, carrying energy that powers nearly every process on Earth. And so, dear cosmic explorers, we've journeyed together through just a small sampling of the remarkable, bizarre, and beautiful phenomena that fill our solar system. From diamond rain on distant ice giants to the slow dance of moons and planets, from the protective embrace of magnetic fields to the violent destruction of sun grazers, our cosmic neighborhood is far stranger and more wonderful than our earthbound imaginations might suggest. Each of these facts represents not just an interesting curiosity, but a piece of the vast puzzle that is our universe. They remind us that we live in a cosmos full of surprises, where the impossible is commonplace and the extraordinary is ordinary. As you drift off tonight, perhaps you'll remember that you're riding on a planet that's spinning through space, orbited by a moon that's slowly moving away, protected by magnetic fields and gas giants, all while travelling around a star in a galaxy that's itself moving through the universe at incredible speeds. We are all, in the most literal sense, children of the cosmos, made of stellar material and shaped by cosmic forces. And there's something deeply comforting in knowing that no matter how vast and strange the universe might be, we're part of it, connected to every star, every planet, and every grain of cosmic dust through the fundamental forces and materials that bind everything together. Sweet dreams, fellow travellers. The universe will continue its magnificent dance while you rest, and tomorrow there will be new wonders to discover. So we've just scratched the surface of our cosmic neighbourhood's strangest secrets. But trust me, we're just getting warmed up here. The solar system has so many more mind-bending surprises waiting for us that, honestly, sometimes I wonder if the universe is just showing off at this point. Also, there are planets in our solar system where it literally rains diamonds. I'm not talking about some poetic metaphor here. I'm talking about actual, honest-to-goodness diamond precipitation falling from alien skies. On Neptune and Uranus, those beautiful blue ice giants lurking in the outer reaches of our solar system, the atmospheric pressure gets so incredibly intense that it can actually crush carbon atoms into diamond crystals. Picture this. You're floating in the thick, churning atmosphere of Neptune, and suddenly you're caught in a downpour of tiny diamonds cascading through the alien sky like the universe's most expensive hailstorm. The process is absolutely wild. Deep in these planets' atmospheres, methane molecules get torn apart by the crushing pressure, which is millions of times stronger than what we experience here on Earth. The carbon atoms from that shredded methane then get squeezed so hard they crystallize into actual diamonds. These precious gems then fall like rain through the dense atmosphere, creating what scientists call diamond precipitation. Now here's the kicker, and this is where it gets really science fiction-y. Some researchers think these diamonds might not even survive the full journey down. As they fall deeper into the planet's interior, the pressure and temperature become so extreme that the diamonds might actually melt into liquid carbon, creating underground seas of liquid diamond. Imagine that for a second. Entire oceans of molten diamonds hidden beneath the clouds of distant worlds. But let's bring things a little closer to home with Fact 32, because apparently our own solar system's weirdness doesn't stop at the outer planets. Mars has the most massive dust storms in the entire solar system, and they can literally engulf the entire planet for months at a time. These aren't your typical desert sandstorms. We're talking about planet-wide atmospheric events that can rage for months, covering every single square kilometre of Martian surface in a thick, choking blanket of dust. The storms are so powerful and so extensive that they completely block out the sun, turning the entire planet into a dark, swirling nightmare. The 2018 dust storm that killed NASA's Opportunity rover is a perfect example of just how brutal these events can be. That storm started as a small regional disturbance, but within weeks it had grown to cover the entire planet. Poor Opportunity, which had been faithfully exploring Mars for almost 15 years, suddenly found itself in perpetual darkness as the storm blocked out the sunlight its solar panels needed to survive. What makes these storms even more incredible is how they can essentially create their own weather. As the dust gets kicked up into the thin Martian atmosphere, it absorbs sunlight and heats up, which creates more wind, which kicks up more dust, which creates more heating. It's like a runaway feedback loop that can sustain itself for months. And here's something that'll blow your mind about Fact 33. There are moons in our solar system that are more geologically active than Earth. I'm looking at you, Io. Jupiter's moon. Io is hands down the most volcanically active body in the entire solar system. This little moon, which is roughly the size of our own moon, has over 400 active volcanoes constantly erupting across its surface. 400! Earth, for comparison, has maybe 50 to 60 active volcanoes at any given time. But Io's volcanoes aren't just numerous, they're absolutely spectacular. Some of these eruptions shoot lava fountains hundreds of kilometers into space. The volcanic plumes are so massive and so energetic that they can be seen from spacecraft millions of kilometers away. The entire surface of Io gets completely resurfaced by volcanic activity every million years or so, which in geological terms is basically yesterday. The reason Io is so incredibly active comes down to a cosmic game of gravitational tug-of-war. Jupiter's immense gravity, combined with the gravitational pull from Io's neighbouring moons Europa and Ganymede, constantly stretches and squeezes Io like a stress ball. This tidal heating generates so much internal friction that the moon's interior stays molten and active. The result is a world that's literally being turned inside out on a regular basis. Io's surface is painted in brilliant yellows, oranges and reds from all the sulfur compounds being constantly spewed out by its volcanoes. It's like a cosmic lava lamp that never stops churning. Speaking of moons that defy expectations, let's talk about Fact 34. Saturn's moon. Enceladus is basically a giant snow globe, and it might be one of the best places in the solar system to look for life. Enceladus looks innocent enough from a distance, just another small icy moon orbiting Saturn. But this little world is hiding an incredible secret beneath its frozen surface. Deep underground, Enceladus has a global ocean of liquid water that's in direct contact with a rocky seafloor. But here's where it gets really exciting. This hidden ocean doesn't just sit there quietly, it's actively venting into space through massive geysers that shoot out from cracks in the moon's south pole. These aren't small water spouts. We're talking about enormous plumes of water vapour and ice particles that spray hundreds of kilometres into space. When NASA's Cassini spacecraft flew through these plumes, it detected something absolutely remarkable: organic molecules. The building blocks of life floating around in the spray from Enceladus's underground ocean. The moon is essentially advertising its potential habitability by shooting samples of its hidden ocean directly into space for us to analyze. The fact that this ocean is in contact with rock is crucial because that interaction could provide the chemical energy needed to support life. On Earth, some of our most extreme ecosystems thrive around hydrothermal vents on the ocean floor, where water interacts with hot rock. Enceladus might have similar environments hidden beneath its icy shell. Now let's venture into fact 35, which is going to make you appreciate just how perfectly positioned Earth really is. Most planets in our solar system have absolutely insane temperature variations that would make life as we know it completely impossible. We've already talked about Mercury's wild temperature swings, but let's put this in perspective. On Venus, the surface temperature is hot enough to melt lead and stays that way pretty much everywhere, all the time. We're talking about 460 degrees Celsius, which is hotter than most pizza ovens. The thick atmosphere traps heat so efficiently that there's basically no temperature difference between day and night, or between the equator and the poles. Mars, on the other hand, can swing from a relatively pleasant 20 degrees Celsius during a summer day at the equator to minus 195 degrees Celsius at the winter poles. That's a temperature range of over 200 degrees, which would be like going from a nice beach day to temperatures colder than dry ice. But the real extremes are out in the outer solar system. On Pluto, temperatures hover around minus 230 degrees Celsius, which is so cold that the atmosphere itself freezes and falls to the ground as snow. Nitrogen snow. Can you imagine? Earth, meanwhile, has this incredible ability to maintain relatively stable temperatures across most of its surface. Sure, we have hot deserts and frozen tundra, but the difference between our hottest and coldest naturally occurring temperatures is only about 140 degrees Celsius. That might sound like a lot, but compared to our planetary neighbours, we're living in a perfectly climate-controlled bubble. Fact 36 is going to take us back to Jupiter, because this giant planet just keeps surprising us. Jupiter has a moon that's bigger than the planet Mercury, and it has its own magnetic field. Ganymede, Jupiter's largest moon, is absolutely massive. With a diameter of about 5,200 kilometers, it's not just the largest moon in our solar system, it's bigger than the planet Mercury. If Ganymede were orbiting the Sun instead of Jupiter, we'd probably classify it as a planet in its own right. But what makes Ganymede truly special is that it's the only moon in the solar system known to have its own magnetic field. This is incredibly rare, and suggests that Ganymede has a molten iron core, just like Earth does. The magnetic field creates auroras at Ganymede's poles, making it the only moon we know of that has its own northern and southern lights. The existence of this magnetic field also tells us something fascinating about Ganymede's interior structure. The moon likely has a layered internal structure with a molten core, a rocky mantle, and multiple layers of ice and liquid water. In fact, scientists believe Ganymede has more water than all of Earth's oceans combined, hidden beneath its icy surface. Let's shift gears with Fact 37 and talk about something that sounds like pure science fiction but is absolutely real. There are places in our solar system where you could literally walk on clouds. Venus has such a dense atmosphere that at certain altitudes, the air becomes thick enough to support human weight. About 50 to 60 kilometers above Venus's hellish surface, the atmospheric pressure and temperature become surprisingly Earth-like. The pressure is similar to what you'd experience at sea level on Earth, and temperatures hover around a comfortable 0 to 60 degrees Celsius. At this altitude, you could theoretically float in the Venusian atmosphere using balloons or airships, and the air would be dense enough that you might be able to walk on specially designed platforms suspended in the clouds. It's like having a habitable zone floating in the sky above one of the most hostile planetary surfaces in the solar system. This concept isn't just theoretical daydreaming. NASA and other space agencies have seriously studied the possibility of floating cities in Venus's upper atmosphere as a way to explore and potentially colonize our neighboring planet. The idea is that we could bypass Venus's toxic surface entirely and build habitats that float in the more hospitable upper atmosphere. The atmospheric composition at this altitude is still pretty nasty, with lots of sulfuric acid in the air, but it's far more manageable than the crushing pressure and molten temperatures at the surface. It's a reminder that habitability in the solar system might not always be where we expect to find it. Fact 38 brings us to one of the most beautiful and mysterious phenomena in our cosmic neighborhood. Some planets have aurora displays that are thousands of times more powerful than Earth's northern lights. Jupiter's auroras are absolutely spectacular. They're not just bigger than Earth's aurora, they're in a completely different league. While Earth's aurora typically extend a few hundred kilometers above our planet's surface, Jupiter's auroral displays can stretch across regions larger than the entire Earth. But it's not just about size. Jupiter's auroras are also incredibly energetic, powered by the planet's massive magnetic field and its rapid rotation. The planet's magnetic field is about 20,000 times stronger than Earth's, and it traps charged particles from the solar wind and from Jupiter's own moons, particularly Io, with all its volcanic activity. The result is an aurora display that's visible not just in visible light, but across the entire electromagnetic spectrum. Jupiter's auroras emit radio waves, ultraviolet light, X-rays, and infrared radiation. If you could see Jupiter's auroras with eyes sensitive to all wavelengths of light, the planet would appear to be crowned with a brilliant, multicolored light show that never stops. Saturn also has incredible auroras, though they're different from Jupiter's. Saturn's auroras are more seasonal, changing as the planet orbits the Sun, and different parts of its atmosphere are illuminated. The auroras interact with Saturn's rings and moons in complex ways, creating patterns and behaviors that scientists are still trying to understand. Now, Fact 39 is going to take us to the very edge of our solar system, where things get really weird. The boundary between our solar system and interstellar space isn't a clean line. It's more like a cosmic traffic jam. The heliopause, which marks the boundary where our sun's influence gives way to interstellar space, isn't a simple barrier. It's a complex, turbulent region where two different types of space weather collide and interact. On one side, you have the solar wind, charged particles streaming out from our sun. On the other side, you have the interstellar medium, particles and radiation from other stars and cosmic sources. When these two forces meet, they create a chaotic boundary layer called the heliosheath. It's like a cosmic mixing zone where particles from our solar system and particles from deep space swirl together in complex patterns. The Voyager spacecraft, which have both crossed this boundary, detected all sorts of unexpected phenomena in this region. The boundary itself moves and shifts depending on solar activity and the density of interstellar space in our local area. During periods of high solar activity, the heliopause can expand outward. When the sun is quieter, it can contract. It's a dynamic breathing boundary that separates our cosmic neighborhood from the rest of the galaxy. What's really mind-blowing is that this boundary acts as a partial shield, protecting our solar system from some types of galactic cosmic radiation. Without this buffer zone, Earth and the other planets would be exposed to higher levels of dangerous radiation from deep space. And finally, let's wrap up this section with Fact 40, which brings us back to our own planet with a humbling reminder of just how connected we are to the rest of the solar system. Earth is constantly being bombarded by tons of space dust every single day. I'm not talking about the occasional meteorite that makes headlines when it lights up the night sky. I'm talking about a constant, gentle rain of microscopic particles from space that's happening right now as you listen to this. Scientists estimate that Earth gains somewhere between 5 and 300 tons of cosmic dust every single day. Most of this dust comes from comets and asteroids. As comets travel through the inner solar system, They leave behind trails of tiny particles that Earth's orbit occasionally intersects. When these particles hit our atmosphere, they usually burn up completely, but they still contribute to Earth's overall mass. Some of this cosmic dust is so small that it doesn't burn up in the atmosphere at all. Instead, it gently settles to Earth's surface, mixing with terrestrial dust and becoming part of our planet's geology. You've probably inhaled particles that originated in the asteroid belt or from the tail of some distant comet. The really fascinating part is that this cosmic dust carries with it the chemical signature of the early solar system. By studying these tiny particles, scientists can learn about the composition and history of our cosmic neighborhood without ever leaving Earth. This constant influx of space material also means that Earth is slowly but steadily growing more massive. It's not a huge change, but over billions of years, this cosmic dust accumulation has contributed to our planet's evolution. We're literally made partly of stardust and space debris, constantly being refreshed with new material from the cosmos. And that's the beautiful thing about our solar system. We're not isolated worlds floating in empty space. We're part of a dynamic, interconnected system where planets influence each other, moons reshape their environments, and even the smallest particles play a role in the ongoing story of our cosmic neighborhood. Every breath you take contains atoms that were forged in the hearts of dying stars. Every step you take is on a planet that's constantly collecting new material from space. You're not just observing the solar system, you're participating in it, part of an ongoing cosmic dance that's been playing out for billions of years. The more we learn about our solar system, the more we realize that the universe is far stranger, more beautiful, and more interconnected than we ever imagined. And we're just getting started. There are still dozens more mind-bending facts waiting for us as we continue our journey through the most incredible neighborhood in the galaxy. Welcome back to our cosmic journey through the most mind-bending truths of our solar system. If you've been following along, you already know that space has a habit of making reality stranger than fiction. We've explored diamond rain, hexagonal storms, and moons with underground oceans. Now let's dive deeper into the bizarre phenomena that make our cosmic neighborhood feel like something out of a science fiction novel. When you think of extreme weather, you might picture hurricanes, tornadoes, or blizzards. But Earth's weather is positively mild compared to what happens elsewhere in our solar system. On Neptune, winds reach speeds of over 2,000 kilometers per hour. That's fast enough to circumnavigate Earth in just 20 hours. These supersonic winds occur despite Neptune receiving only 1,000th of the sunlight that Earth gets. Scientists still don't fully understand how such weak solar energy can drive such incredibly violent storms. Venus takes extreme weather to another level entirely. Its atmosphere is so dense that the pressure at the surface is equivalent to being nearly a kilometre underwater on Earth. The temperature reaches 465 degrees Celsius, hot enough to melt lead. But perhaps most unsettling is the rain. On Venus, it rains sulfuric acid. These corrosive droplets never reach the surface because they evaporate in the intense heat about 25 kilometres up, creating a perpetual acid storm cycle in the upper atmosphere. Mars does experience snowfall, but it's unlike anything you'd see on Earth. Martian snow comes in two varieties, water ice snow and carbon dioxide snow. The water ice snow is more familiar, falling from clouds just like on Earth, though it usually sublimes before reaching the surface. The carbon dioxide snow is far more alien. It falls as dry ice crystals, particularly near the polar regions during winter. This frozen carbon dioxide accumulates into seasonal polar caps that grow and shrink dramatically with the Martian seasons. What makes this even more fascinating is that Mars experiences dust snow as well. Dust particles can become electrically charged and form cohesive flakes that drift down from the thin atmosphere. Some of this dust snow can travel vast distances, contributing to the planet-wide dust storms that can last for months and completely obscure the surface from orbital view. Titan, Saturn's largest moon, hosts the most Earth-like weather system in the solar system, with one major difference. Instead of water, everything runs on liquid methane. Titan has methane clouds, methane rain, methane rivers, and methane lakes. It even experiences methane hurricanes, with spiral structures that mirror tropical storms on Earth. The methane cycle on Titan is remarkably similar to Earth's water cycle. Methane evaporates from the surface lakes, rises into the dense nitrogen atmosphere, condenses into clouds, and falls as rain. This rain carves river channels, fills lakes, and creates seasonal weather patterns. Some of these methane storms can cover areas larger than the Great Lakes and produce rainfall rates that would make Earth's heaviest downpours seem like drizzle. What's particularly mind-bending is that Titan's atmosphere is so dense and its gravity so low that humans could actually fly with wings attached to their arms. If you could survive the minus 180 degrees Celsius temperature and breathe methane, you could literally soar through alien storm systems. Io is the most volcanically active body in the solar system, with over 400 active volcanoes. But these aren't ordinary volcanoes. Due to Io's low gravity and lack of atmosphere, volcanic eruptions can launch material 500 kilometers into space. That's higher than the International Space Station orbits Earth. Some of these eruptions are so powerful, they create umbrella-shaped plumes visible from spacecraft millions of kilometers away. The volcanic activity is so intense that Io's surface is completely resurfaced every few thousand years. The moon is literally turning itself inside out on a geological timescale. The lava temperatures reach up to 1800 degrees Celsius, hotter than most volcanic activity on Earth. The sulfur-rich composition creates a landscape painted in vivid yellows, oranges, and reds that would look perfectly at home in an alien world from science fiction. This extreme volcanism is powered by tidal heating from Jupiter's immense gravity, which flexes Io like a stress ball as it orbits. The constant stretching and squeezing generates enough internal heat to keep the moon's interior molten and drive the most spectacular fireworks show in the solar system. Saturn's magnificent rings, perhaps the most iconic feature in our solar system, are not permanent. They're actively falling into the planet like cosmic rain. Scientists call this ring rain, and it's happening at a rate of about 10,000 kilograms per second. At this rate, the rings could completely disappear in just 100 to 300 million years. The Cassini spacecraft discovered that this ring material, composed primarily of water ice, gets electrically charged by ultraviolet light and magnetic fields. This charge causes the particles to spiral inward towards Saturn's atmosphere, where they vaporize. The process is so significant that it's actually affecting Saturn's upper atmosphere and contributing to the planet's overall composition. Even more remarkable is the possibility that Saturn's rings are relatively young in astronomical terms. Some evidence suggests they may have formed just 100 to 200 million years ago, meaning we're living during a brief cosmic moment when Saturn has rings. Dinosaurs may have looked up at a ringless Saturn, and our distant descendants might see one again. While we don't have this in our solar system, astronomers have discovered exoplanets where the weather defies all earthly logic. HD 18973b, located 63 light-years away, experiences sideways glass rain, driven by winds of 8,700 kilometers per hour. The extreme temperatures cause silicate particles to condense into glass droplets that are then hurled horizontally by supersonic winds. This discovery has revolutionized our understanding of what planetary atmospheres can do. It's a reminder that our solar system, bizarre as it may seem, is actually quite tame compared to some of the cosmic weather systems that exist elsewhere in the galaxy. This sounds impossible, but Mercury harbors substantial deposits of water ice at its poles. Despite surface temperatures reaching 430 degrees Celsius during the day, the planet's polar regions contain permanently shadowed craters where temperatures never rise above -170 degrees Celsius. These cosmic freezers have been accumulating ice for potentially billions of years. The ice likely came from comet impacts over Mercury's history. When comets struck other parts of the planet, the water vapor could migrate to these permanently cold regions and freeze solid. Some estimates suggest there could be between 100 billion and 1 trillion tons of ice hidden in Mercury's polar shadows. This ice is so well preserved that it might contain a record of the early solar system's water delivery system. It's like finding prehistoric ice samples in the cosmic equivalent of the world's most extreme freezer. Mars does experience aurora, but they're fundamentally different from the northern and southern lights we see on Earth. While Earth's aurora occur in oval patterns around the magnetic poles, Martian aurora can appear anywhere on the planet and take on bizarre shapes that would look alien to Earth observers. Because Mars lacks a global magnetic field, its aurora are created by interactions between solar particles and localized magnetic fields embedded in the planet's crust. These fossil magnetic fields are remnants from when Mars had a global magnetic field billions of years ago. The result is aurora that can appear as discrete spots, serpentine shapes, or diffuse glows scattered across the Martian sky. Even stranger, Mars experiences proton aurora created by hydrogen atoms from the solar wind. These aurora occur on the day side of the planet and are invisible to human eyes, detectable only by ultraviolet instruments. It's like Mars has its own secret light show, happening in wavelengths we can't see. Enceladus, one of Saturn's moons, hosts some of the most spectacular geysers in the solar system. These aren't hot water geysers like those in Yellowstone, but rather fountains of ice particles and water vapor that shoot hundreds of kilometers into space from the moon's south polar region. The geysers emerge from 4 parallel fractures nicknamed tiger stripes that are warmer than the surrounding terrain. The water comes from a subsurface ocean beneath Enceladus's icy crust, and when it reaches the surface, through these cracks, it explosively vaporizes in the vacuum of space. What makes this even more fascinating is that these geysers contain organic molecules, suggesting that the subsurface ocean might have the ingredients for life. The Cassini spacecraft actually flew through these plumes and tasted them, finding complex organic compounds that formed naturally in space. It's like having a natural space probe sampling an alien ocean for us. Jupiter's immense gravity makes it the solar system's janitor, sweeping up potentially dangerous objects that might otherwise threaten the inner planets. The planet has been observed capturing comets and asteroids, sometimes dramatically. In 1994, astronomers watched as comet Shoemaker-Levy 9 broke apart and crashed into Jupiter in a series of impacts that left dark scars larger than Earth. Computer simulations suggest that without Jupiter's gravitational influence, Earth would experience significantly more impacts from asteroids and comets. Jupiter's position and mass create a kind of gravitational shield that deflects many objects away from the inner solar system or captures them entirely. However, Jupiter's influence isn't always protective. Sometimes its gravity can also redirect objects toward the inner planets. But statistical analysis shows that, overall, Jupiter prevents far more impacts than it causes, making it a net benefit for Earth's long-term survival. Several moons in our solar system have retrograde orbits, meaning they orbit in the opposite direction of their planet's rotation. Triton, Neptune's largest moon, is the most famous example. It orbits Neptune backwards, which strongly suggests that Triton was originally an independent object, possibly from the Kuiper belt, that was captured by Neptune's gravity. This backward orbit is gradually causing Triton to spiral inward toward Neptune. In about 3.6 billion years, Triton will either crash into Neptune or be torn apart by tidal forces, potentially creating a spectacular ring system around the planet that could rival or exceed Saturn's rings. Many of the outer moons of the giant planets also have retrograde orbits. These are thought to be captured asteroids or comets that were snared by the planet's gravity fields. Their backward motion tells the story of the chaotic early solar system, when gravitational encounters could dramatically alter the fate of entire worlds. Just like comets develop tails when they approach the Sun, our entire solar system has a tail as it moves through the galaxy. This tail, called the heliotail, is created by the interaction between the solar wind and the interstellar medium. As our solar system travels through space at about 100,000 kilometers per hour, the heliosphere, the bubble of solar wind that surrounds us, gets compressed in front and stretched out behind, creating a comet-like shape. The tail extends for billions of kilometers behind us as we journey through the galaxy. The Voyager spacecraft have provided some of our best data about this phenomenon as they've travelled beyond the edge of the heliosphere. Understanding our solar system's tail helps us comprehend how star systems interact with the broader galactic environment and how they're shaped by their motion through space. It might seem impossible for such small objects to have their own gravitational companions, but many asteroids are actually binary or even triple systems. The asteroid Ida, for example, has a small moon called Dactyl that orbits it every 20 hours. These asteroid moons probably formed through several different mechanisms. Some may be the result of collisions that broke off chunks of material that remained gravitationally bound. Others might be separate objects that were captured when they passed too close to a larger asteroid. The study of asteroid moons helps scientists understand the internal structure and composition of asteroids. By observing how these tiny moons orbit, researchers can calculate the mass and density of the parent asteroid, providing insights into whether they're solid rocks, loose rubble piles, or something in between. The solar system has what amounts to a spacecraft graveyard. When missions to Mars fail, many end up in this region of space between Earth and Mars, where failed spacecraft drift in solar orbits. Over the decades, this area has accumulated a collection of human-made objects that didn't quite make it to their destinations. Some of these objects follow orbital paths that occasionally bring them back near Earth, where they're sometimes mistaken for asteroids until their artificial origin is recognized. It's a sobering reminder that space exploration is difficult and that the solar system now contains artifacts of our attempts to explore it. This cosmic junkyard also includes upper stages of rockets, pieces of spacecraft that broke apart, and even tools that astronauts have accidentally lost during spacewalks. While space is vast and these objects pose little danger, they represent humanity's growing presence in the solar system. Ancient Mars was a dramatically different world. Geological evidence shows that billions of years ago, Mars had a much thicker atmosphere and liquid water flowing on its surface. Valley networks, delta formations, and mineral deposits all point to a time when Mars was warm and wet. The planet likely lost its atmosphere through a combination of factors, including the loss of its global magnetic field, which allowed solar wind to strip away atmospheric particles. This process took hundreds of millions of years, gradually transforming Mars from a potentially habitable world into the cold, dry planet we see today. Some scientists believe that early Mars might have been more hospitable to life than early Earth. While our planet was being pummeled by massive asteroid impacts during the late heavy bombardment, Mars may have provided a more stable environment for life to emerge and evolve. Olympus Mons on Mars is not just large, it's impossibly massive by Earth standards. This shield volcano stands 21 kilometers high, nearly 3 times taller than Mount Everest, and covers an area roughly the size of the state of Arizona. Its base is so wide that if you stood on one edge, the opposite edge would be beyond the horizon. The volcano grew to such enormous size because Mars lacks plate tectonics. On Earth, volcanic hotspots eventually move as tectonic plates shift, creating chains of volcanoes like the Hawaiian Islands. On Mars, volcanic hotspots stay in one place, allowing single volcanoes to grow to colossal proportions over billions of years. Despite its enormous size, Olympus Mons has very gentle slopes, typically only 2 to 5 degrees. You could drive a car up most of its surface without difficulty. The gentle slopes are characteristic of shield volcanoes, which form from fluid lava flows rather than explosive eruptions. Beneath Europa's icy surface lies an ocean that may contain twice as much water as all of Earth's oceans combined. But what makes this subsurface sea truly remarkable is that it might be more suitable for life than our own oceans. Europa's ocean is kept liquid by tidal heating from Jupiter's gravity, which provides a consistent energy source independent of sunlight. The ocean likely has contact with a rocky seafloor, where chemical reactions could provide nutrients and energy for potential life forms. The ice shell above acts like a protective barrier, shielding the ocean from Jupiter's intense radiation, while still allowing some exchange of materials through cracks and upwelling. This creates a stable environment that might have persisted for billions of years, far longer than life has existed on Earth. Titan's hydrocarbon lakes and seas contain hundreds of times more liquid hydrocarbons than all of Earth's known oil and natural gas reserves. These aren't fossil fuels like on Earth, but rather hydrocarbons that formed through atmospheric chemistry in Titan's thick, methane-rich atmosphere. The liquid methane and ethane on Titan's surface represents an enormous energy resource, though obviously not one we could practically access. The total volume of hydrocarbons on Titan exceeds 40,000 cubic kilometers, making it the largest known repository of hydrocarbons in the solar system. This abundance of organic molecules makes Titan one of the most chemically interesting places in the solar system. The Moon essentially serves as a natural laboratory for studying organic chemistry on a planetary scale, providing insights into the types of chemical processes that might have occurred on early Earth. Some asteroids are essentially flying mountains of pure metal, composed primarily of iron and nickel. These metallic asteroids, like 16 Psyche, are thought to be the exposed cores of ancient protoplanets that were stripped of their rocky mantles by massive collisions early in the solar system's history. 16 Psyche alone is estimated to contain more iron, nickel, and precious metals than the entire global economy has ever mined. If we could somehow bring all that material to Earth, it would be worth more than the global economy many times over, though it would also completely crash commodity markets. These metallic asteroids provide unique insights into planetary formation. They represent the building blocks of rocky planets, the cores that would have been buried deep inside larger worlds if those worlds had fully formed. Studying them is like performing an autopsy on a failed planet. Despite containing hundreds of thousands of known asteroids, the asteroid belt is mostly empty space. If you were to travel through it, you'd be unlikely to see even one asteroid with the naked eye. The average distance between asteroids in the main belt is about 1 million kilometers, roughly 3 times the distance from Earth to the Moon. This emptiness extends throughout the solar system. The distance scales are so vast that even our largest planets are just tiny specks in an ocean of vacuum. If Earth were the size of a marble, the Moon would be a peppercorn 7.5 meters away, and the Sun would be a 2.5 meter sphere, located 1 kilometer distant. This emptiness is actually crucial for the stability of planetary orbits. If space were more crowded, gravitational interactions would make the solar system chaotic and unstable. The vast distances between objects allow them to follow predictable paths for billions of years. As we continue our journey through the cosmos, these incredible facts remind us that our solar system is far stranger and more wonderful than our everyday experience might suggest. From ice-spewing moons to planets where glass rains sideways, from asteroid moons to disappearing rings, the universe consistently proves that reality is more imaginative than fiction. Each of these phenomena represents not just a curious fact, but a window into the fundamental physics that governs our cosmic neighborhood. They challenge our assumptions about how worlds can behave and expand our understanding of what's possible in the vast theater of space. The solar system continues to surprise us and undoubtedly holds many more secrets waiting to be discovered by future generations of explorers and scientists. Part 4. 50 things about the solar system that sound fake but are totally real. Let's keep diving deeper into the cosmic madness because, honestly, the more we discover about our solar system, the more it feels like someone's playing an elaborate prank on us. I mean, we've already covered planets that rain diamonds and moons with underground oceans, but trust me, we're just getting started. The universe has a serious sense of humor, and it's about to get even weirder. Here's something that'll mess with your head. Asteroids, those cosmic rocks floating around in space, can have their own tiny moons orbiting them. We're talking about rocks orbiting rocks, like some kind of celestial Russian nesting doll situation. Take asteroid Ida, for example. This potato-shaped chunk of space debris, about 56 kilometers long, has its own little companion called Dactyl that's only about 1.4 kilometers across. It's like finding out your pet hamster has a pet ant. The gravitational forces at play here are so delicate that if you threw a baseball too hard on Ida, you might accidentally launch it into orbit around the asteroid. These binary asteroid systems form through various processes. Sometimes a larger asteroid breaks apart. Sometimes two asteroids get captured in each other's gravitational embrace during a cosmic slow dance. Venus continues to be the absolute champion of this shouldn't be possible, but here we are. Those mysterious bright patches on Venus's highest peaks, they're not water snow, ice snow, or even carbon dioxide snow. They're metal snow, specifically lead sulfide and bismuth sulfide that condenses out of the atmosphere at high altitudes where it's slightly cooler. Picture this. On a planet where the surface temperature can melt lead, the mountaintops are actually cool enough for metallic compounds to freeze out of the air and dust the peaks like some kind of toxic winter wonderland. It's like nature's most hardcore frost, where instead of delicate ice crystals, you get heavy metal compounds settling on the landscape. Only Venus would find a way to make snow more dangerous than the 900-degree surface temperature. Saturn's moon Mimas has a crater so large and perfectly positioned that it looks exactly like the Death Star from Star Wars. The Herschel crater is about 130 kilometers across on a moon that's only 400 kilometers in diameter. That's like having a crater the size of England on an object the size of Spain. But here's the kicker. The impact that created this crater nearly shattered Mimas completely. The shock waves from the collision travelled around the moon and created fractures on the exact opposite side. If the impactor had been just slightly larger, we wouldn't have a Death Star look-alike. We'd have had a pile of cosmic rubble. It's one of those cosmic coincidences that makes you wonder if George Lucas had insider information about Saturn's moons. Jupiter isn't just the largest planet in our solar system. It's basically our cosmic bodyguard, acting like a giant gravitational vacuum cleaner that hoovers up dangerous comets and asteroids before they can cause problems for the inner planets. We've actually watched this happen. In 1994, comet Shoemaker-Levy 9 broke apart and slammed into Jupiter in a spectacular display that left dark scars in the planet's atmosphere for months. Each impact released energy equivalent to millions of hydrogen bombs. Without Jupiter's massive gravitational influence, that comet might have ended up heading toward Earth instead. Scientists estimate that Jupiter reduces the number of dangerous impacts on Earth by a factor of about 1,000. It's like having a cosmic bouncer that keeps the really dangerous stuff away from the VIP section where we live. Though occasionally, Jupiter's gravity can also fling things toward us. Overall, we owe our gas giant neighbour a serious debt of gratitude. Olympus Mons on Mars is so ridiculously large that it breaks your brain when you try to comprehend it. This shield volcano is about 22 kilometers high. That's roughly 2.5 times taller than Mount Everest. But the height is just the beginning of its absurdity. The base of Olympus Mons is about 600 kilometers across. If you placed it on Earth, it would cover most of France. The volume is so enormous that you could fit the entire chain of Hawaiian Islands inside it with room to spare. The summit caldera alone is 80 kilometers wide. You could lose entire cities in there. The reason Mars can support such massive volcanoes is that it doesn't have plate tectonics like Earth. On Earth, the crust moves around, so volcanic hotspots create chains of smaller volcanoes as the plates drift. On Mars, the crust stays put, so lava just keeps piling up in the same spot for millions of years, creating these absolutely monstrous mountains that dwarf anything we have on Earth. Triton, Neptune's largest moon, is basically the rebel of the solar system because it orbits in the opposite direction to Neptune's rotation. This retrograde orbit is like swimming upstream in the cosmic river, and it tells us that Triton probably wasn't born around Neptune at all. Scientists believe Triton was originally a dwarf planet from the Kuiper Belt, possibly similar to Pluto, that got too close to Neptune and was gravitationally captured. This cosmic kidnapping story is written in Triton's backwards orbit and its unusual composition, which matches other Kuiper Belt objects more than typical moons. But here's the really wild part. Triton's retrograde orbit means it's slowly spiraling inward toward Neptune. In about 3.6 billion years, it's going to get so close that Neptune's gravity will tear it apart, potentially creating a spectacular ring system around the ice giant. It's like a very, very slow-motion, cosmic car crash that we get to watch unfold over geological time. Enceladus, one of Saturn's moons, shoots enormous geysers of water ice hundreds of kilometers into space from cracks near its south pole. These aren't little spurts. We're talking about massive plumes that create one of Saturn's rings as the ice particles spread out and orbit the planet. But Enceladus isn't alone in this cosmic water show. Jupiter's moon, Europa, likely has similar geysers, and even distant Triton around Neptune has geysers of nitrogen gas shooting up from its surface. What makes these geysers possible is tidal heating. The gravitational squeezing and stretching these moons experience as they orbit their massive parent planets generates enough internal heat to keep subsurface oceans liquid and create pressure that drives these spectacular eruptions. The Cassini spacecraft actually flew through Enceladus's plumes and tasted the water, finding not just H2O, but also organic molecules and salts that suggest a warm, salty ocean beneath the ice. It's like the universe is serving up samples of potentially habitable environments on a silver platter, shooting them into space for us to analyze. Uranus and Neptune have magnetic fields that are completely bonkers. Instead of being aligned with their rotation axes like Earth's magnetic field, theirs are tilted at crazy angles. Uranus's magnetic field is tilted 59 degrees from its rotational axis, and Neptune's is tilted 47 degrees. It's like their magnetic north poles are having an identity crisis. Even weirder, these magnetic fields don't originate from the center of the planets. Like you'd expect, they're offset significantly from the core, suggesting they're generated in the outer layers of these ice giants rather than deep in their centers. This creates magnetic field geometries that are completely unlike anything we see on Earth, Mars, or Jupiter. These bizarre magnetic configurations might be the result of these planets' unusual compositions and internal structures. Unlike the rocky planets or gas giants, Uranus and Neptune have complex interiors filled with water, methane, and ammonia ices under extreme pressure, creating exotic forms of matter that might generate magnetic fields in completely unexpected ways. Saturn's moon Enceladus has a density so low that it's basically a giant snowball held together by its own gravity. With a density of just 1.6 grams per cubic centimetre, it's only slightly denser than water, which means it's composed almost entirely of water ice with just a small rocky core. But this cosmic snowball is far from boring. Despite being only 500 kilometres across, Enceladus is one of the most geologically active bodies in the solar system. Its south polar region is covered with tiger stripes, massive cracks in the ice that spew water vapour and ice particles into space. The surface near these cracks is relatively crater-free, indicating it's constantly being renewed by fresh ice. The energy for all this activity comes from tidal heating, as Saturn's gravity kneads Enceladus like cosmic bread dough. This generates enough heat to maintain a subsurface ocean beneath the ice shell, making this tiny moon one of the most promising places to search for extraterrestrial life in our solar system. Jupiter isn't just the king of the planets by size, in fact, it's also the ruler of the largest moon collection in the solar system. As of the latest count, Jupiter has at least 95 confirmed moons, and astronomers keep finding more. Most of these are tiny irregular chunks of rock and ice, probably captured asteroids, but the sheer number is staggering. The four largest, Io, Europa, Ganymede and Callisto, discovered by Galileo, are each fascinating worlds in their own right. Ganymede is larger than Mercury and has its own magnetic field. Europa and Callisto likely have subsurface oceans. Io is the most volcanically active body in the solar system. But beyond these famous four, Jupiter has dozens of other moons, with orbital periods ranging from 7 hours to more than 3 years. Some of these outer moons orbit in groups that share similar orbital characteristics, suggesting they're fragments of larger bodies that were broken apart by collisions. It's like Jupiter collected a whole asteroid belt's worth of objects and kept them as pets, creating a complex gravitational dance that's still revealing new members to this day. Earth isn't alone in its journey around the Sun. We have cosmic companions called Trojan asteroids that travel along the same orbital path, staying roughly 60 degrees ahead of or behind our planet. These asteroids hang out at gravitational sweet spots called Lagrange points, where the combined gravity of Earth and the Sun creates stable parking zones. The first Earth Trojan asteroid was discovered in 2010 and named 2010 TK7. It's about 300 meters across and follows a complex horseshoe-shaped path that keeps it in Earth's L4 Lagrange point. Finding these objects is incredibly difficult because they are always close to the Sun's direction from Earth's perspective, making them nearly impossible to spot with ground-based telescopes. Jupiter has thousands of known Trojan asteroids, and Mars and Neptune have them too, but Earth's Trojans are particularly hard to find and study. They represent pristine samples of the early solar system that have been preserved in these gravitational safe havens for billions of years, making them valuable targets for future exploration missions. Most people picture comets as having a single tail streaming behind them, but many comets actually develop two distinct tails as they approach the Sun, and these tails point in different directions. The dust tail is made of heavier particles that follow the comet's orbital path, while the ion tail is composed of charged gas particles that are blown directly away from the Sun by the solar wind. This creates the bizarre situation where a comet can have one tail pointing roughly backward along its orbit and another tail pointing directly away from the Sun, regardless of the comet's direction of travel. During certain parts of the orbit, these tails can even point in nearly opposite directions, giving the comet a forked appearance. Some comets develop even more complex tail structures. Comet McNaught in 2007 developed multiple streamers and a spectacular fan-shaped dust tail that was visible to the naked eye. The interaction between the comet's outgassing, the solar wind, and the comet's rotation can create intricate patterns that change day by day as the comet moves through space. Saturn's rings aren't just pretty cosmic jewelry. They're a complex dynamic system where the planet's moons act like cosmic shepherds, creating gaps, waves, and intricate patterns in the ring material. The most famous example is the Cassini division, a prominent gap in the rings caused by gravitational resonances with the moon Mimas. Some of Saturn's smaller moons, called shepherd moons, orbit within or near the rings and use their gravity to keep ring particles in line. Pan, for example, orbits within the Encke gap and sweeps up ring material, creating propeller-like disturbances. These moons are like cosmic vacuum cleaners, maintaining clear channels through the ring system. Even more fascinating are the spokes, mysterious dark radial features that appear and disappear in Saturn's B-ring. These are thought to be caused by electrostatic forces that lift tiny dust particles above the main ring plane, creating temporary ghostly patterns that rotate with the planet's magnetic field rather than following orbital mechanics. HD 1897333b, while technically an exoplanet and not in our solar system, represents the kind of hellish weather that makes Venus look like a pleasant vacation spot. This planet has winds that reach 8,700 kilometers per hour. That's more than 6 times the speed of sound on Earth. But the really nightmarish part is what's in those winds: tiny particles of silicate glass. The extreme temperatures and pressures on this planet cause silicon-based compounds to condense into glass particles in the atmosphere. These glass shards are then whipped around by the supersonic winds, creating a permanent sandstorm of razor-sharp glass moving at hypersonic speeds. It's like being inside a blender filled with broken bottles during a Category 5 hurricane. While this particular planet isn't in our solar system, it gives us perspective on just how weird and hostile planetary atmospheres can get. It makes you appreciate that even though Venus has sulfuric acid clouds and Mars has global dust storms, at least we don't have to worry about sideways glass rain. Asteroid Itokawa, visited by Japan's Hayabusa spacecraft, has such low density that it's essentially a pile of rubble held together by weak gravity. With a density of only 1.9 grams per cubic centimetre, this asteroid is about 40% empty space. It's like a cosmic Swiss cheese, made of rock instead of dairy. These rubble pile asteroids are thought to be the result of previous collisions that shattered larger asteroids, with the fragments eventually reaccumulating into loose collections of rocks and boulders. The gravity is so weak that if you were standing on Itokawa and threw a baseball with normal Earth strength, it would escape the asteroid's gravity and fly off into space. This discovery has major implications for planetary defense. If we ever need to deflect a dangerous asteroid heading for Earth, we can't just nuke it like in the movies. That might just turn one big rubble pile into lots of smaller rubble piles still heading our way. Instead, we'd need gentler techniques like gravitational tractors or ion beam shepherds to slowly nudge these cosmic loose rock collections off course. Mars does have auroras, but they're nothing like the beautiful curtains of light we see at Earth's poles. Because Mars doesn't have a global magnetic field like Earth, its auroras appear as scattered patches of light that can pop up anywhere on the planet. Not just near the poles. These Martian auroras are caused by the solar wind directly interacting with the planet's thin atmosphere, and they often occur near regions where ancient magnetic fields are still embedded in the crust, remnants from when Mars had a global magnetic field billions of years ago. It's like the planet's magnetic memory is still glowing in the dark. Even stranger, Mars has auroras that extend much higher into the atmosphere than Earth's, and they're often invisible to the human eye, glowing primarily in ultraviolet light. The European Space Agency's Mars Express orbiter has captured images of these ghostly light shows, revealing a planet where the northern lights can appear in the middle of the day at the equator. Saturn's moon, Iapetus, looks like someone took a bite out of a cosmic apple and then glued the pieces back together wrong. This moon has a bizarre two-tone coloration. One hemisphere is as dark as charcoal, while the other is as bright as fresh snow. But the really weird part is its shape. Apatus has a massive ridge that runs around its equator like a cosmic walnut, giving it a distinctly non-spherical appearance. This ridge is about 20 kilometers high and 1,300 kilometers long, making it one of the most dramatic topographical features in the solar system relative to the body's size. If Earth had a proportional feature, it would be a mountain range 200 kilometers high, circling the equator. The origin of this ridge is still debated. Some scientists think it might be the remains of a ring system that collapsed onto the moon's surface, while others suggest it formed from internal geological processes. Either way, Iapetus looks like no other moon in the solar system, a cosmic oddball that seems to have been assembled from spare parts. The Great Red Spot, Jupiter's most famous feature, has been shrinking for over a century. When it was first observed in detail in the late 1800s, it was large enough to fit 3 Earths side by side. Today, it's only about 1.3 times Earth's diameter, and it's continuing to shrink at an accelerating pace. But even as it shrinks, the Great Red Spot is getting taller and more intense. It's like a cosmic tornado that's becoming more concentrated as it contracts. The wind speeds at its edge can reach 680 kilometers per hour, and the storm extends deep into Jupiter's atmosphere, possibly hundreds of kilometers down. Scientists aren't sure if the Great Red Spot will eventually disappear completely or if it will stabilize at a smaller size. Computer models suggest it might break apart into smaller storms or merge with other atmospheric features. We might be witnessing the end of a storm system that has raged for centuries, making us lucky to observe this iconic feature before it potentially vanishes forever. Cryovolcanoes, or ice volcanoes, erupt slushes of water, ammonia, and other volatiles instead of molten rock. These have been found on several moons in the outer solar system, including Enceladus, Titan, and Triton. Instead of lava, they spew mixtures that would be liquid at the extremely cold temperatures of these distant worlds. On Enceladus, these cryovolcanoes create the spectacular geysers that feed Saturn's E-ring. On Titan, they might help explain the moon's smooth plains and the presence of atmospheric methane. On Triton, nitrogen geysers shoot dark material high into the thin atmosphere, creating visible plumes that can be tracked from orbit. These ice volcanoes are powered by tidal heating, radioactive decay, or other internal heat sources that can melt subsurface ices. They're essentially cosmic slush machines that reveal the complex geology possible on worlds where water behaves like rock and liquid methane flows like water. While not in our solar system, most stars in the galaxy exist in binary or multiple star systems, meaning planets orbiting them would experience sunrises and sunsets involving multiple suns. These Tatooine-like worlds would have complex seasonal patterns and day-night cycles that would make Earth's climate seem boringly simple. In our own solar system, we only have one sun, but we do have some interesting multiple-body gravitational relationships. The Pluto-Charon system is essentially a double dwarf planet where both bodies orbit around a common centre of mass that lies between them. If you were standing on Pluto, Charon would hang motionless in the sky, always showing the same face, like a second moon that never moves. Some of the outer solar system objects exist in binary pairs, including several Kuiper belt objects that orbit each other while simultaneously orbiting the Sun. These cosmic dance partners show us that gravitational relationships in the solar system are far more complex and varied than the simple planet-orbiting star model we learned in school. Hyperion, another of Saturn's moons, looks like a cosmic bath sponge that's been pockmarked with craters. Its surface is so porous and irregular that it has one of the lowest densities of any solid body in the solar system. It would float in water if you could find a bathtub big enough. This bizarre appearance is the result of Hyperion's low gravity and composition. When meteoroids impact its surface, Instead of creating typical bowl-shaped craters, they punch deep, narrow holes that don't fill in or erode away. The result is a surface that looks like it's been attacked by a cosmic hole punch, creating a honeycomb texture unlike anything else in the solar system. Hyperion also has chaotic rotation, meaning it tumbles unpredictably as it orbits Saturn instead of keeping one face pointed toward the planet like most moons. This chaotic tumbling is caused by its irregular shape and gravitational interactions with Saturn and nearby Titan, making it essentially a cosmic pinball bouncing through space. The Sun produces magnetic tornadoes that can be hundreds of times larger than Earth. These twisted magnetic field lines create rotating columns of plasma that spiral upward from the Sun's surface at speeds of up to 300,000 kilometers per hour. They're like cosmic hurricanes made of superheated gas and magnetic fields. These solar tornadoes can channel material from the Sun's surface up into its corona, contributing to the heating of the outer atmosphere and the acceleration of the solar wind. Some of these magnetic vortices can persist for hours or even days, creating spectacular displays when viewed through specialized solar telescopes. The magnetic field lines in these tornadoes can become so twisted and tangled that they eventually snap and reconnect, releasing enormous amounts of energy in solar flares and coronal mass ejections. It's like the Sun is constantly experiencing magnetic weather that makes Earth's most powerful storms look like gentle breezes. The asteroid Chariklo, located between Saturn and Uranus, has its own ring system, making it the smallest known body in the solar system to possess rings. These rings were discovered when Chariklo passed in front of a star, and astronomers noticed additional dips in brightness before and after the main occultation. Chariklo's rings are incredibly thin and narrow, only about 7 kilometers wide, but they orbit the 250-kilometer asteroid at a distance of about 400 kilometers. The rings are likely made of debris from impacts on the asteroid's surface, or possibly from a small moon that was destroyed by tidal forces. This discovery opened up the possibility that rings might be more common in the solar system than previously thought. Several other small bodies have since been found to have ring systems, suggesting that any object with sufficient gravity might be able to capture and maintain orbiting debris under the right conditions. The Kuiper Belt, beyond Neptune's orbit, is home to countless icy bodies that are essentially dormant comets waiting for gravitational perturbations to send them careening toward the inner solar system. But there's also a place where active comets go to fade away, the region near Jupiter where the gas giant's immense gravity can capture comets and force them into short-period orbits. These Jupiter family comets get trapped in the inner solar system, making repeated close approaches to the Sun that gradually boil away their volatile materials. Each orbit strips away more ice and gas until they're reduced to dark, rocky remnants that look more like asteroids than comets. It's a cosmic recycling process that turns bright, active comets into dead rocks over just a few thousand years. Some asteroids in the inner solar system are probably extinct comets that have lost all their volatile materials. They're like cosmic ghosts, retaining the orbital characteristics of comets, but lacking the spectacular tails and comas that make comets so dramatic. It's a reminder that the solar system is constantly evolving, with objects changing categories and characteristics over time. As our entire solar system moves through the galaxy at about 220 kilometers per second, it creates a massive bow shockwave in the interstellar medium, like a cosmic boat pushing through the galactic ocean. This heliospheric bow shock was predicted by models, but has been difficult to observe directly because of our position inside the system. The bow shock forms because the solar wind from our Sun creates a bubble in space called the heliosphere, and as this bubble plows through the interstellar medium, it pushes aside gas and dust, creating a shockwave ahead of us. This shockwave is enormous, potentially spanning several light years across. Recent observations from the Voyager spacecraft and other missions have provided evidence for this bow shock, showing that our solar system creates its own wake as it travels through the galaxy. It's like discovering that our entire cosmic neighborhood is essentially a giant spaceship sailing through the sea of interstellar space, leaving a trail of disturbed gas and magnetic fields in its wake. The structure of this bow shock depends on the density of the interstellar medium we're currently traveling through and the strength of the solar wind. As we move through different regions of the galaxy over millions of years, the shape and intensity of our bow shock changes, potentially affecting the amount of cosmic radiation that reaches the inner solar system and even influencing Earth's climate over geological timescales. What makes this even more mind-bending is that we're essentially surfing through the galaxy on a wave of solar wind, protected by a magnetic bubble that our sun creates. The heliosphere acts like a cosmic force field, deflecting most galactic cosmic rays and creating a relatively safe zone for life to evolve and thrive. Without this protection, Earth would be bombarded by much higher levels of dangerous radiation from deep space. And there you have it, 50 absolutely bonkers facts about our solar system that sound like they came from a science fiction writer's fever dream, but are completely verifiably real. From diamond rain on ice giants to metal snow on Venus, from moons that orbit backwards to asteroids with their own moons, from planets where glass rains sideways to volcanoes that erupt ice instead of lava, our cosmic neighborhood is far stranger and more wonderful than anything we could have imagined just a few decades ago. What's perhaps most amazing is that these discoveries keep coming. Every new space mission, every improved telescope, every innovative instrument reveals new mysteries that challenge our understanding of how planetary systems work. We've found subsurface oceans on moons we thought were dead, active geology on worlds that should be frozen solid, and complex chemistry in places where life might actually be possible. The solar system isn't just a collection of predictable, well-behaved celestial objects following neat orbital mechanics. It's a dynamic, chaotic, endlessly surprising cosmic laboratory where the laws of physics play out in ways that constantly surprise and delight scientists. Every world tells a different story of formation, evolution, and the incredible creativity of natural processes operating over billions of years. Perhaps the most humbling thing about all these discoveries is how much we still don't know. Despite centuries of observation and decades of space exploration, we're still finding fundamental surprises in our own cosmic backyard. If our solar system, the one place in the universe we've studied most intensively, can still shock us with new discoveries, imagine what secrets are waiting to be uncovered in the thousands of other planetary systems we're now discovering around distant stars. The universe, it turns out, has an absolutely incredible imagination, and we're just getting started on reading the stories it has written in ice and rock, gas and plasma, gravity and magnetism across the vast expanse of space and time. Every mission to every world reveals that reality is far more extraordinary than fiction. And that's perhaps the most wonderful discovery of all. So the next time you look up at the night sky, remember that you're not just looking at pretty lights in the darkness. You're looking at a cosmic carnival of impossible worlds where the rules of reality are stretched to their absolute limits, where the ordinary becomes extraordinary, and where every new discovery reminds us that we live in a universe far more amazing than we ever dared to dream. Continuing our exploration of the solar system's most astounding secrets, we now venture into realms where moons defy expectations. Magnetic fields create cosmic shields, and the very structure of space itself resonates with hidden harmonies. The phenomena we're about to uncover might sound like pure science fiction, but they're unfolding right now in our cosmic neighborhood. When most people think of Jupiter's moons, they picture the famous 4 Galilean satellites, Io, Europa, Ganymede, and Callisto. But Jupiter's family is far more extensive and bizarre than anyone imagined. The gas giant currently boasts over 90 confirmed moons, with new ones discovered regularly as our telescopes become more sensitive. What makes this moon collection truly extraordinary isn't just the sheer number, it's the chaotic variety of their behaviours. Some of Jupiter's moons orbit in the opposite direction to the planet's rotation, a phenomenon called retrograde motion. These rebellious satellites likely represent captured asteroids or fragments from ancient collisions. Their backwards dance a testament to the violent history of our solar system's formation. The smallest of these moons are barely a few kilometers across, irregular chunks of rock and ice that tumble through space in wildly eccentric orbits. Some venture so far from Jupiter that they take over 2 Earth years to complete a single orbit, while others huddle close to their massive parent. The diversity is staggering. Volcanic Io spews sulfur into space, while icy Europa hides a subsurface ocean deeper than any on Earth. Deep in the outer solar system, where sunlight barely provides warmth, one of Saturn's smaller moons has become a beacon of biological possibility. Enceladus, just 500 kilometers in diameter, harbours one of the most exciting discoveries in planetary science: massive geysers erupting from its south pole, launching plumes of water vapour and organic compounds hundreds of kilometers into space. The Cassini spacecraft flew directly through these plumes and made a discovery that changed everything. The geysers contain not just water ice, but complex organic molecules including formaldehyde, acetylene, and propane. Even more intriguing, the spacecraft detected tiny silica particles that could only form through hydrothermal activity on the ocean floor, suggesting hot springs beneath Enceladus's icy surface. This small moon possesses a global ocean containing more water than all of Earth's oceans combined, kept liquid by tidal heating from Saturn's immense gravity. The combination of liquid water, organic chemistry, and energy sources makes Enceladus one of the most promising places to search for extraterrestrial life. Its geysers provide a convenient sampling mechanism, essentially delivering potential signs of life directly to visiting spacecraft. While Earth's weather systems are powered by water, Mars operates on an entirely different principle: dust. The red planet hosts dust devils that dwarf any tornado on Earth, some reaching heights of 20 kilometers and spanning several kilometers in width. These towering vortices are so massive they can be seen from orbit, leaving dark trails across the Martian landscape as they scour the surface. Unlike Earth's tornadoes, which form from severe thunderstorms, Martian dust devils arise from simple thermal convection. The thin atmosphere and extreme temperature differences between day and night create perfect conditions for these phenomena. As the surface heats up during the day, columns of warm air rise rapidly, picking up the fine, iron-rich dust that gives Mars its distinctive colour. Some dust devils on Mars are electrically charged, generating lightning-like discharges as particles collide within the vortex. These electrical storms can interfere with spacecraft electronics and may play a role in the planet's atmospheric chemistry. The dust devils also act as natural cleaning mechanisms for solar panels on Mars rovers, occasionally sweeping away accumulated dust and extending mission lifetimes. Venus continues to defy expectations with yet another atmospheric peculiarity: lightning that behaves completely opposite to Earth's electrical storms. While terrestrial lightning typically travels from clouds toward the ground, Venusian lightning predominantly strikes upward, from the surface toward the dense, sulfuric acid clouds above. This inverted electrical behavior stems from Venus's extreme atmospheric conditions. The surface pressure is 90 times greater than Earth's, creating a dense, electrically conductive environment. The planet's thick atmosphere contains sulfur compounds that become highly ionized, generating electrical fields with polarities opposite to what we experience on Earth. The lightning on Venus is also far more frequent and intense than Earth's storms. The thick atmosphere acts like a massive electrical capacitor, storing charge before releasing it in spectacular upward discharges. These electrical storms may play a crucial role in Venus's atmospheric chemistry, breaking down complex molecules and contributing to the planet's hostile surface conditions. Jupiter doesn't just dominate the solar system through gravity, it wields a magnetic field so powerful it creates a radiation environment that would kill an unprotected human in minutes. This magnetic field is approximately 20,000 times stronger than Earth's and extends so far into space that it would appear larger than the Moon if we could see it from Earth. The source of this incredible magnetic power lies deep within Jupiter's interior, where liquid metallic hydrogen acts as a massive electrical conductor. As Jupiter spins rapidly, completing a rotation in just under 10 hours, this conductive layer generates electrical currents that create the most powerful planetary magnetic field in the solar system. This magnetic monster traps charged particles from the solar wind, accelerating them to incredible energies and creating radiation belts that extend far beyond Jupiter's moons. The radiation levels near Io, Jupiter's innermost large moon, are so intense they would deliver a fatal dose to a human in less than an hour. Even the heavily shielded Juno spacecraft requires special protection to operate in this harsh environment, and its mission is deliberately limited in duration to prevent radiation damage. One of the solar system's most iconic features is temporary. Saturn's magnificent rings, which have captivated observers since Galileo first glimpsed them through his telescope, are slowly spiraling into the planet and will completely disappear in roughly 300 million years. This cosmic vanishing act is happening right before our eyes, though the timescale makes it invisible to human perception. The rings are primarily composed of water ice particles, ranging in size from tiny grains to house-sized chunks. These particles are constantly bombarded by micrometeoroids and charged particles, which knock material out of orbit. Additionally, Saturn's magnetic field creates an electrical connection with the rings, causing charged ring particles to spiral inward along magnetic field lines. The Cassini spacecraft measured this ring rain directly, finding that Saturn is consuming its rings at a rate of about 2,000 kilograms per second. This discovery suggests that Saturn's rings are much younger than previously thought, possibly forming only 100–200 million years ago when a moon or large asteroid was torn apart by tidal forces. We're witnessing Saturn during a brief, spectacular phase of its existence. Uranus is the solar system's oddball, rolling along its orbital path like a ball rather than spinning like a top. This unique 98-degree axial tilt means the planet essentially lies on its side, causing extreme seasonal variations where each pole experiences 42 years of continuous sunlight followed by 42 years of darkness. The most widely accepted explanation for this bizarre orientation is a catastrophic collision early in the solar system's history. A Mars-sized object likely struck Uranus with tremendous force, knocking it over and fundamentally altering its rotational axis. This ancient impact may have also contributed to the formation of Uranus's moon system and its unusual magnetic field, which is tilted 59 degrees from the planet's rotational axis. The collision theory is supported by computer simulations showing that such an impact could produce Uranus's current configuration without destroying the planet entirely. The aftermath of this cosmic collision continues to influence Uranus today, creating the most extreme seasonal cycles in the solar system and contributing to the planet's remarkably bland appearance due to its unusual atmospheric circulation patterns. At the edge of our solar system, where sunlight provides barely 1/1000th the energy it delivers to Earth, Neptune hosts the fastest winds in the solar system. These atmospheric rivers race around the planet at speeds exceeding 2,000 kilometers per hour, faster than the speed of sound in Neptune's atmosphere, creating truly supersonic weather systems. This phenomenon puzzles scientists because wind speeds typically correlate with available energy, and Neptune receives minimal solar heating. The answer lies in the planet's internal heat source. Neptune radiates 2.6 times more energy than it receives from the Sun, suggesting powerful internal processes generate the energy driving these incredible winds. The source of Neptune's internal heat remains mysterious. Unlike Jupiter and Saturn, which still retain heat from their formation, Neptune should have cooled off long ago. Some theories suggest radioactive decay in the core, while others propose that the planet's interior undergoes phase transitions that release energy. These supersonic winds create and maintain atmospheric features like the Great Dark Spot, storm systems comparable in size to Jupiter's Great Red Spot, but far more dynamic and short-lived. The asteroid belt isn't just populated by solitary chunks of rock drifting through space. Many asteroids have gravitationally captured smaller companions, creating binary or even triple asteroid systems that orbit each other in a cosmic dance. These asteroid moons, or moonlets, demonstrate that gravitational relationships exist at every scale in the solar system. The first asteroid moon was discovered in 1993 when the Galileo spacecraft observed tiny dactyl orbiting the asteroid Ida. Since then, astronomers have identified hundreds of binary asteroids, with some systems featuring multiple small moons orbiting a larger parent body. These relationships form through various mechanisms: gentle collisions that create debris, tidal capture of passing objects, or the breakup of larger asteroids that leave gravitationally bound fragments. Some asteroid moons orbit incredibly close to their parents, completing orbits in just hours, while others maintain distances similar to Earth-Moon separations. The study of these systems provides crucial insights into asteroid composition, internal structure, and the early history of the solar system. They also present unique challenges for spacecraft navigation, as missions must account for complex gravitational fields when approaching binary asteroid systems. Mars today is a cold, dry world with a thin atmosphere, but geological evidence reveals a dramatically different past. Early in its history, Mars possessed a global magnetic field similar to Earth's, generated by a molten iron core and active dynamo processes. This magnetic shield protected the planet's atmosphere from solar wind erosion and may have allowed liquid water to persist on the surface for extended periods. Approximately 4 billion years ago, Mars's magnetic field mysteriously shut down. The planet's core cooled and solidified, ending the dynamo process that had generated the protective magnetic field. Without this shield, the solar wind began stripping away Mars's atmosphere, gradually transforming it from a potentially habitable world into the barren landscape we see today. Remnants of Mars's ancient magnetic field are preserved in the planet's crust, particularly in the southern highlands. These magnetic signatures, detected by orbiting spacecraft, create a patchwork pattern that tells the story of Mars's magnetic history. Some regions retain strong magnetic fields that create mini-magnetospheres, providing localized protection from radiation and offering clues about the planet's more hospitable past. The discovery of Mars's magnetic history has profound implications for astrobiology. During the period when Mars had a magnetic field, the planet likely maintained a thicker atmosphere and stable liquid water on its surface. This represents a window of time, lasting perhaps 1 billion years, when Mars might have been habitable for life as we know it. As we conclude this section of our journey through the solar system's most incredible phenomena, we're reminded that our cosmic neighborhood is far more dynamic and interconnected than early astronomers could have imagined. From backwards orbiting moons to supersonic winds on distant planets, each discovery reveals new layers of complexity in the grand symphony of gravitational, magnetic, and atmospheric forces that shape our solar system. These aren't just abstract scientific curiosities, they're clues to understanding how planetary systems form and evolve, how life might arise elsewhere in the universe, and how the delicate balance of forces that make Earth habitable came to be. Every moon that shoots geysers into space, every magnetic field that shields or fails to shield a world, every wind that races across alien skies adds another note to our growing understanding of the cosmic processes that govern not just our solar system, but potentially countless others throughout the galaxy. Welcome back, fellow space travelers, to part 6 of our incredible journey through the solar system's most mind-bending secrets. We've already explored diamond rain on distant worlds, underground oceans hidden beneath icy crusts, and volcanoes that dwarf anything on Earth. But trust me, we're just getting warmed up. The cosmos has saved some of its most spectacular tricks for this chapter, and what we're about to discover will challenge everything you think you know about how our celestial neighborhood actually works. Today we're diving into phenomena so extraordinary that if you saw them in a science fiction movie, you'd probably roll your eyes and say, "Come on, that's ridiculous." But here's the beautiful truth about our universe. Reality is far stranger than fiction could ever dare to be. We're talking about planets that spin backwards, moons that orbit in impossible directions, and gravitational sweet spots where we park our most important telescopes. We're going to explore worlds where a single day lasts longer than an entire year, and discover why one of our gas giants could literally float in your bathtub if you had a bathtub the size of a planet. But perhaps most fascinating of all, we'll uncover how the solar system is constantly reshaping itself in ways that operate on timescales so vast they make human civilization look like a brief flicker. Mountains of ice that appear and vanish, atmospheric cycles that span decades, and cosmic dances between worlds that have been choreographed by gravity itself over billions of years. What makes these discoveries so captivating isn't just their sheer impossibility, but how they reveal the delicate, interconnected nature of everything around us. Every bizarre rotation, every backwards orbit, every floating gas giant tells a story about violence and beauty, chaos and order, destruction and rebirth. These aren't just random quirks of physics. They're the scars and signatures of a solar system that has been shaped by catastrophic collisions, gravitational battles, and the slow, patient work of time itself. So buckle up, because we're about to visit worlds where the very concept of normal gets thrown out the window. We'll discover places where gravity creates perfect parking spots in space, where entire planets tumble through their orbits like cosmic footballs, and where the line between solid and liquid becomes beautifully blurred. The solar system isn't just our neighborhood, it's a collection of natural laboratories running experiments that we're only just beginning to understand. Let's start with something that sounds like science fiction, but is happening right now, just 1.5 million kilometers away from Earth. There's a point between our planet and the Sun where gravity balances perfectly, and that's where we put some of our most important telescopes to watch the cosmos. This magical spot is called Lagrange Point L1, and it's like finding the perfect sweet spot on a cosmic seesaw. At this location, the gravitational pull of Earth and the Sun cancel out in such a precise way that objects can stay in a stable position relative to both bodies. It's not that gravity disappears, it's that the competing forces create a kind of gravitational parking space where spacecraft can hover with minimal fuel consumption. The beauty of L1 is that it allows continuous observation of the Sun or deep space without interruption. Satellites placed there can monitor our star 24/7, helping to predict solar flares and coronal mass ejections that might affect Earth. The SOHO spacecraft has been stationed at L1 for decades, serving as our early warning system for space weather that could knock out satellites or disrupt power grids. But L1 isn't just a parking spot, it's a window into the fundamental forces that shape our solar system. Objects there don't just sit motionless, they orbit around the balance point in graceful patterns called halo orbits. It's like watching gravity perform ballet, creating stable paths where you'd least expect them. What's truly remarkable is that these Lagrange points exist throughout the solar system, wherever two massive objects create their gravitational dance. They're invisible highways and rest stops scattered throughout space, waiting for us to discover and utilize them. Each one tells a story about how mass and motion can create pockets of stability in what might otherwise be chaotic orbits. Now, speaking of things that challenge our expectations, let's visit a world where time itself seems to have gotten confused. On Venus, a day is longer than its entire year, creating one of the most mind-bending temporal puzzles in our solar system. Venus rotates so slowly that it takes about 243 Earth days to complete one full spin on its axis. But here's the kicker. It only takes about 225 Earth days for Venus to orbit the Sun once. This means that if you could somehow survive on Venus's surface, you'd experience a sunset, then wait through an entire Venusian year and still be waiting for the next sunrise. It's like the planet got stuck in cosmic molasses while continuing its journey around the Sun. But wait, it gets even weirder. Venus doesn't just spin slowly, it spins backwards. If you could stand on its surface and watch the sun rise, it would appear in the west and set in the east. This retrograde rotation makes Venus one of only 2 planets in our solar system that spins in the wrong direction, and scientists are still debating exactly how this happened. The most likely explanation involves a catastrophic collision early in Venus's history. Imagine a Mars-sized object slamming into the young planet with such force that it not only reversed its spin, but slowed it down to a crawl. It's a reminder that our solar system's early days were far more violent and chaotic than the relatively peaceful orbits we see today. This bizarre rotation has profound effects on Venus's climate and atmosphere. The planet doesn't experience the kind of day-night cycle that drives weather patterns on Earth. Instead, its thick atmosphere circulates in ways that create a runaway greenhouse effect, making Venus the hottest planet in the solar system, despite being farther from the Sun than Mercury. Speaking of unexpected properties, let's talk about Saturn, the planet that could float in water. This sounds like something a science teacher might say to get your attention, but it's absolutely true. Saturn is the least dense planet in our solar system, with an average density of about 0.687 grams per cubic centimetre, which is less than water's density of 1.0. If you had a bathtub large enough, Saturn would indeed float. Of course, such a bathtub doesn't exist outside of thought experiments, but the principle holds. This low density comes from Saturn's composition. It's mostly hydrogen and helium, the lightest elements in the universe. Its massive volume spreads out this low-mass material, creating an average density that's surprisingly low for such a giant planet. What makes this even more fascinating is that Saturn is still incredibly massive, about 95 times more massive than Earth. But size matters too, and Saturn's huge volume means all that mass is distributed across an enormous space. It's like the difference between a bowling ball and a beach ball filled with feathers. They can have very different densities despite both being spherical. This low density contributes to Saturn's rapid rotation and distinctive shape. The planet spins so fast that it completes a full rotation in just over 10 hours, causing it to bulge significantly at the equator and flatten at the poles. It's the most visibly oblate planet in our solar system, looking more like a cosmic beach ball that someone sat on than a perfect sphere. The concept of a floating planet might sound whimsical, but it reveals something profound about planetary formation and composition. Saturn formed in the cold outer regions of the solar system, where light gases could accumulate without being blown away by solar radiation. It's a reminder that planets come in varieties we're still learning to understand, from dense rocky worlds to fluffy gas giants that challenge our intuitions about what a planet should be. Now let's journey to Jupiter, where storms rage for centuries and weather patterns make Earth's hurricanes look like gentle breezes. Jupiter's Great Red Spot is perhaps the most famous storm in the solar system, a massive anticyclonic tempest that has been continuously observed for over 400 years. This isn't just a big storm, it's a weather system so large that 2 or 3 Earths could fit inside it. The Great Red Spot maintains wind speeds of over 400 kilometers per hour, sustained by Jupiter's internal heat and the complex dynamics of its atmosphere. Unlike storms on Earth, which are broken up by land masses and changing surface conditions, Jupiter's storms can persist for centuries because the planet has no solid surface and generates enormous amounts of internal energy. What keeps these storms going is Jupiter's unique atmospheric structure. The planet has powerful jet streams that trap and channel storm systems, preventing them from dissipating. The Great Red Spot sits between 2 of these jet streams like a cosmic ball bearing, maintained by the very forces that might otherwise tear it apart. Recent observations from the Juno spacecraft have revealed that these storms extend much deeper into Jupiter's atmosphere than previously thought. The Great Red Spot may penetrate hundreds of kilometers below the visible cloud tops, making it more like a deep, atmospheric river than a surface weather pattern. It's a 3-dimensional storm system of staggering complexity and scale. The colours of Jupiter's storms remain something of a mystery. The Great Red Spot's distinctive hue might come from chemicals like phosphorus or sulfur compounds altered by ultraviolet radiation from the sun. Different altitudes in the atmosphere create different chemical conditions, leading to the layered, multicolored appearance that makes Jupiter's storms so visually striking. These eternal storms serve as natural laboratories for understanding fluid dynamics on a massive scale. They help scientists model atmospheric behavior not just on other gas giants, but on exoplanets around distant stars. Jupiter's weather systems are so extreme and long-lasting that they provide insights into atmospheric physics that we simply can't obtain anywhere else. Moving from Jupiter's organized chaos to something far more unpredictable, let's visit Hyperion, one of Saturn's most bizarre moons. This irregularly shaped satellite looks like a cosmic sponge, or perhaps a natural spacecraft, and it spins in a completely chaotic way that defies the orderly rotation we see in most other moons. Hyperion is about 270 kilometers across and has a density so low, only about 0.55 grams per cubic centimeter, that it's likely made mostly of ice, with a lot of empty space. This porous structure gives it a sponge-like appearance, with deep, sharp-edged craters that don't follow the usual patterns we see on more solid bodies. What makes Hyperion truly unique is its chaotic rotation. Unlike other moons, which typically become tidally locked to show the same face to their parent planet, Hyperion tumbles unpredictably. Its axis of rotation changes randomly as it orbits Saturn, meaning there's no consistent day or night, and sunlight hits different parts of the moon in completely unpredictable patterns. This chaotic behavior results from Hyperion's irregular shape and its gravitational interactions with nearby Titan, Saturn's largest moon. The competing gravitational influences, combined with Hyperion's non-spherical form, create a tumbling motion that's impossible to predict over long periods. It's like trying to predict how an oddly shaped rock will bounce down a hill, except the hill is made of gravitational fields, and the bouncing continues for millions of years. The surface of Hyperion is electrically charged due to interactions with Saturn's magnetic field. Particles from the planet's magnetosphere give the Moon a mild electrostatic environment, which could affect how dust moves across its surface. This makes Hyperion not just visually unique, but electrically active as well. From Hyperion's chaos, let's travel to the edge of our solar system to explore another surprising possibility. Pluto may have underground liquid oceans even though it's incredibly far from the Sun. This idea challenges our assumptions about where liquid water can exist and what constitutes a potentially habitable environment. Despite surface temperatures of about 230 degrees Celsius, features on Pluto's surface suggest geological activity that could only be explained by movement below the crust. The New Horizons mission revealed cracks, ridges, and resurfaced plains that indicate something is pushing and pulling at the icy shell from beneath. The key to Pluto's potential ocean lies in radioactive decay within its rocky core. Even though the dwarf planet is small and distant, the decay of radioactive elements could provide enough heat to keep water liquid if it's insulated by thick layers of ice. The ocean, if it exists, would be trapped under dozens or even hundreds of kilometers of ice, containing salts or ammonia that act like antifreeze to keep it from freezing solid. One of the most compelling pieces of evidence is Sputnik Planitia, a massive icy basin that appears to be sinking into Pluto's interior. This behavior could only happen if there's a dense liquid layer beneath the surface, providing the buoyancy and flow patterns that explain the basin's current position and orientation. Pluto's potential ocean wouldn't be unique. Many icy bodies in the outer solar system, from Europa to Enceladus, are thought to harbour subsurface seas. What's remarkable is how common liquid water might be in environments that seem impossibly hostile to life as we know it. These hidden oceans expand our definition of habitable zones far beyond the traditional Goldilocks zone around stars. If Pluto does have an underground ocean, it represents a fascinating example of how internal heat sources can maintain liquid environments long after a world has moved far from its star's warmth. It suggests that habitable conditions might persist in places we never thought to look, hidden beneath frozen surfaces in the dark corners of solar systems. Now let's explore one of the most geometrically perfect and baffling features in our solar system, Saturn's hexagonal North Pole. At Saturn's North Pole, there's a gigantic hexagon-shaped jet stream that circles the pole continuously. This six-sided pattern was first spotted by Voyager in the 1980s and has remained stable for decades, defying easy explanation. The hexagon is about 30,000 kilometers wide, larger than Earth, and it's a stable, long-lasting feature in the planet's atmosphere. It's not a surface structure, but a cloud pattern that rotates with the planet and maintains its geometric shape, despite the chaotic nature of atmospheric dynamics. Wind speeds inside the hexagon exceed 300 kilometers per hour, creating a fast-moving jet stream that somehow curves into perfect straight edges instead of the circular patterns we'd normally expect. The reason for this hexagon remains one of planetary science's great mysteries. Laboratory experiments with rotating fluids have created similar polygon shapes, suggesting it results from fluid dynamics and the interaction of winds at different latitudes. But why Saturn's hexagon is so large, stable, and precisely six-sided remains unclear. What makes it even more puzzling is that there's no corresponding hexagon at Saturn's south pole. The southern pole has a more conventional circular vortex, like a hurricane. This asymmetry makes the northern hexagon even harder to explain and suggests that specific conditions, perhaps related to seasonal heating or internal dynamics, are required to create and maintain this geometric precision. The hexagon extends deep into Saturn's atmosphere, possibly hundreds of kilometers below the visible cloud tops. Infrared observations reveal that it's not just a surface phenomenon, but a deep-seated atmospheric structure. There's also a massive storm sitting right in the center of the hexagon at the North Pole, with its own eye and spiral structure, though it doesn't move in sync with the hexagonal pattern. This geometric precision in a chaotic fluid environment represents one of nature's most striking examples of order emerging from apparent randomness. It's a reminder that atmospheric dynamics can create patterns and structures that seem almost artificially designed, even though they arise from purely natural processes. Speaking of impossible-sounding phenomena, let's venture to Neptune and Uranus, where it literally rains diamonds. Deep inside these ice giants, extreme pressure and temperature conditions may cause carbon atoms to crystallize and fall like precipitation through the planet's interiors. The atmospheres of Neptune and Uranus are rich in methane, which contains carbon. Deep inside these planets, pressures reach millions of times Earth's atmospheric pressure. Under these conditions, the pressure is so intense that it can crush carbon atoms into diamond crystals. Scientists believe that methane molecules break apart under these extreme conditions, and the carbon atoms reform as solid diamond, which then falls like rain through the planet's interior. This isn't happening in the upper atmosphere where we can observe it, but thousands of kilometers below the surface, in layers where the pressure is high enough to compress carbon into its crystalline form. Laboratory experiments have successfully simulated these conditions using high-powered lasers, actually creating diamond crystals by compressing hydrocarbons under extreme pressure. The diamonds probably don't stay intact forever. As they fall deeper into the planet's interiors, they may melt or dissolve in the liquid layers below, but the continuous formation and precipitation of diamonds could contribute to heat generation and energy flow inside these distant worlds. This diamond rain might help explain why Uranus and Neptune emit less internal heat than Jupiter and Saturn. The process of diamond formation could trap energy, or the friction of falling diamonds might contribute to internal heating in ways we're still trying to understand. These exotic weather patterns show how different planetary environments can create chemical processes that seem almost magical. The idea of diamond rain sounds like fantasy, but it's supported by solid physics and laboratory evidence. It reminds us that the outer solar system hosts phenomena so extreme that they stretch our imagination while remaining firmly grounded in natural law. From diamond rain, let's move to an environment so hostile that it crushes most spacecraft within minutes: Venus's surface. Venus has one of the most extreme atmospheres in our solar system, with a surface pressure about 92 times higher than Earth's and temperatures hot enough to melt lead. The atmosphere is made mostly of carbon dioxide with clouds of sulfuric acid, creating a crushing, corrosive environment that destroys most human-made objects quickly. The Soviet Venera missions in the 1970s and 1980s were the only spacecraft to successfully land and transmit data from Venus's surface, with the longest surviving lander operating for just about 2 hours. The extreme conditions result from a runaway greenhouse effect. Venus's thick atmosphere traps heat so efficiently that the surface temperature reaches about 465 degrees Celsius, making it hotter than Mercury despite being farther from the Sun. The dense air doesn't just create pressure problems, it also blocks visible light, making the surface perpetually dim despite the intense heat. What makes Venus particularly challenging for exploration is that the harsh conditions exist at multiple levels. The sulfuric acid clouds start about 50 kilometers above the surface, While the crushing pressure and heat dominate the lower atmosphere and surface, any mission must be protected against chemical corrosion, extreme heat, and enormous pressure simultaneously. The thick atmosphere also creates unusual effects. Objects fall slowly through the dense air, and the surface experiences very little temperature variation between day and night or between different locations. The entire planet maintains a nearly uniform, hellish temperature that never varies by more than a few degrees. Despite these challenges, Venus remains one of the most scientifically valuable targets in our solar system. Its similarity to Earth in size and composition makes it a crucial case study for understanding how planets can evolve along dramatically different paths. Future missions are being designed with advanced materials and cooling systems that might allow longer survival on the surface, but Venus will always remain one of the most hostile environments we know. Now let's journey to Titan, Saturn's largest moon, where we find the most Earth-like landscape in the solar system, but made of completely different materials. Titan has rivers, lakes and seas, but they're all made of liquid methane and ethane instead of water. At Titan's extremely low temperatures, around 179 degrees Celsius, methane behaves like water does on Earth. It evaporates, forms clouds and rains back down, creating a complete methane cycle that mirrors Earth's water cycle. This creates familiar-looking landscapes of valleys, drainage systems, and even what appear to be deltas, but carved by flowing hydrocarbons instead of water. Titan has seasons, and its weather changes over time. Scientists have observed storms and rainfall events in different regions depending on the season. Dark streaks across the surface suggest recent rainfall, while radar images reveal extensive lake systems, especially near the poles. Some of these methane seas are hundreds of kilometers wide and surprisingly deep. The largest of these seas, Kraken Mare, is bigger than the Great Lakes combined and has been measured to be at least 300 meters deep in places. Titan even has islands that may appear and disappear, possibly due to floating chunks of ice or changes in liquid levels due to seasonal effects. What makes Titan so remarkable is that it's the only moon in our solar system known to have stable liquid on its surface and a thick atmosphere. The combination creates weather patterns, erosion, and geological processes that make it more like a planet than a typical moon. Its orange sky, dense atmosphere, and active surface processes create a world that's both alien and strangely familiar. Titan also shows signs of having a subsurface water ocean beneath its icy crust, potentially creating two completely different environments for studying planetary processes, one based on methane chemistry at the surface, and another based on water chemistry below ground. Let's wrap up this section by exploring Mercury, a world of extremes where temperatures swing from 170 degrees Celsius at night to 430 degrees Celsius during the day. This represents one of the widest temperature ranges in our solar system, and it's all due to Mercury's lack of a substantial atmosphere. Mercury has only a thin exosphere made of atoms blasted off its surface by solar wind and micrometeoroid impacts. This wispy envelope can't trap heat like Earth's atmosphere, so once the sun sets, heat escapes into space rapidly. The planet's slow rotation makes this effect even more extreme, with each side experiencing long periods of heating or cooling. During the day, Mercury receives about 7 times the intensity of sunlight that Earth does. The rocky surface absorbs this energy directly, with no clouds or atmospheric scattering to provide relief. Surface temperatures soar to levels that can melt some metals, creating an environment more hostile than the inside of many ovens. At night, without any atmospheric insulation, temperatures plummet to levels colder than anywhere on Earth's surface. This constant thermal cycling creates enormous stress on Mercury's rocks and contributes to unique erosion patterns caused not by wind or water, but by the endless expansion and contraction of the surface materials. Surprisingly, Mercury's polar regions contain permanently shadowed craters that are cold enough to preserve water ice, despite the planet's proximity to the Sun. These regions never see direct sunlight and serve as cold traps where ice can survive for billions of years, creating some of the coldest spots in the inner solar system on one of the hottest planets. These extreme temperature swings make Mercury a natural laboratory for studying how materials behave under intense thermal stress. The planet serves as a testing ground for understanding surface processes on airless worlds and helps us prepare for missions to other rocky bodies throughout the solar system. As we conclude this chapter of our cosmic journey, we've seen how the solar system constantly surprises us with phenomena that challenge our understanding of how worlds can behave, from floating gas giants to diamond rain, from backward spinning planets to geometric storm patterns. Each discovery reveals new layers of complexity and beauty in our celestial neighborhood. These aren't just cosmic curiosities, they're windows into the fundamental processes that shape planetary systems everywhere. Every backwards rotation tells a story of ancient collisions. Every stable Lagrange point reveals the elegant mathematics of gravity, and every extreme environment expands our understanding of where and how complexity can emerge in the universe. The more we explore our solar system, the more we realize that reality truly is stranger than fiction. From diamond rain on Neptune to underground oceans on distant moons, these incredible phenomena remind us that we're living in a cosmic neighborhood filled with wonders that challenge our imagination and expand our understanding of what's possible. Each new discovery not only reveals the extraordinary complexity of planetary physics, but also hints at the potential for life in places we never thought to look. As our technology advances and our exploration continues, one thing is certain: the solar system will keep surprising us with facts that sound absolutely impossible but are beautifully, undeniably real.